This is screencast 5 for week 3 for Business Administration 571. I had some comments I was talking about at the end of the last screencast. Another comment is that you should automate and or computerize the collection and updating of a control chart or sets of control charts. So you've heard of a dark factory. That's where they turn all the lights off because the robots don't need them. The robots are building stuff and there's nobody there other than maybe one or two maintenance people or maybe a person up in some control room. All metrics, of course, are automatically observed and sent to real-time programs. IBM has a sensor network initiative. So for lots of money, they will come in and put sensors on key parts on your production line, and they'll route everything back to a server, and the control chart will be updated automatically. In addition, the control chart will, if it gets signal, it will broadcast that event to appropriate personnel. So you definitely should not be trying to build these control charts by hand. You shouldn't even be running them yourself with software. You should have the software connected to the sensors directly, and the control chart should be updated by an overarching supervisor program. Another point is, since normality of x bar I is assumed. Why? Is it? Well, yeah, you're assuming that to build the control limits. You should check this assumption in stage 1 by constructing a normal QQ plot of x1 through lowercase x1 through lowercase xk. So if strong violations are noted, then a transformation should be tried. You will you will do a QQ plot homework problem in the homework out of Ryan's chapter 3. To get you back remembering how to get a QQ plot. Well, what's this transformation? If you have a violation in your QQ plot, and that is that you have the z-scores down here, and you have x bar sorted here, and you get something like this, then you may need, kind of got overlap there, didn't it? You may need to raise x to some power, which is on the unit interval. So if you raise x to the square root power 0.5, then you're taking the square root of every number that's coming off of your sensor, and you may get better normality. So this indicates lack of normality. Another thing you can do is increase n. So I'll say or increase n, because the central limit theorem guarantees that if you have n big enough, the distribution of these subgroup means are going to start looking like the sampling distribution. Rather, that sampling distribution will actually start looking like a normal distribution. But you may not be able to increase n big enough to get normality to start happening with an n value that is still feasible for you to acquire information out of control in a timely manner. So you may need to do some transformations to get normality to be more or less satisfied with a humble or a modest n, say 3 or 4. Okay. In Ryan, he mentions something called an AR1. This is for autoregressive. Autoregressive process of order 1. I'm going to come back to this, so you don't need to know about it right now, but he does mention it, assuming that you know what that is. I've got a heads up on that in my PDF file called charts.pdf out on the G drive. So like I say, this is not something you need to know about now, but if you're wondering what is going on and how come he is assuming that you know this phrase, it's something from time series analysis, and that's a little bit advanced for this course, but we're going to need to know a tiny bit about it downstream a couple of weeks from now, actually 3 or 4 weeks from now. So just kind of keep in the back of your mind that there is some words out of me on what that is. Now, an example. Let's apply these ideas to a service operation. Let's say we want to evaluate Navy pilots and decide who gets to keep flying and who doesn't. So you got your aircraft carrier here, and you have your jet plane coming in, and there are wires that the plane, with its little hook, will grab one of these wires, and those wires will slow it down before it falls off the end of the aircraft carrier. Now, it is recommended that that hook hits the deck somewhere here. The reason is that'll catch the number 2 wire, as it's called, cable. It's not so easy to do that, though, because since the aircraft carrier is in the ocean, it's bouncing around, and the plane is falling out of the sky, literally. But basically, the plane is in a state of stall because the engines are wound up tight. So the plane's coming in a very difficult to control situation. The reasons the engines are wound up as high as they can go is because if the landing has to be aborted, you have to be at near full throttle in order to get back up in the air before you fall into the water. So basically what you do is you stall the plane, but you keep the engines wound up high, and as you stall, you fall, and you basically fall onto the carrier. And so this takes a certain amount of skill to do. And so what happens is up here in the little control room, you have a fellow pilot, actually 3, and they're watching you as you fly your plane in, and they're taking notes. And when you're all done landing and you get together, they give you their notes on how you did. Now, they are your peers, so you can't say, "Who are you to tell me how to land a plane?" because they do it also. Now, they say, "Not a very good landing, guy. Hope you do better next time." If they say that a couple of times to you, guess what happens? You are rotated back to the States, and you get to practice landings on good old dry land until you get better. And the expression is, a Navy pilot is only as good as their last landing. Well, that's actually true about a lot of people in the service industry. It doesn't really matter what you've done a long time ago. All that matters is what is your most recent performance level. So you've decided to instrument this problem. And you've decided to measure the distance from the back end of the carrier to where the wheels hit. So this is wheel hit distance. So you've got a sweet spot in here that you're hoping that they'll hit. But depending on variation in pilot performance, weather, conditions, weight of the plane, how much fuel is still in the plane, there's going to be variability as to exactly where those wheels actually hit. So you're going to start monitoring this. You're going to run a control chart on what? You're not running it on the planes or the carriers. You're running it on the human. You're running it on the pilot. So this is a great example of a service industry application. I think it's a great example. Why do surgeons retire in their late 50s? Because their hands don't work as well. You don't want somebody cutting away on your heart who doesn't have as steady a hand anymore. And so basically, surgeons leave their profession when they become unreliable as surgeons. Well, same for Navy pilots, same for a lot of people who have a high performance and demanding service operation. Okay, so let's run SAS to analyze some data that we took on this process. Now, if you think about it, you can take this, you can run this control chart for each pilot or for all pilots together. Or you can run it over a certain period of time for all pilots or just one pilot. Well, so let's say we're running it one control chart for each pilot. And we're in theater, and so we're doing a lot of landings. So we're getting a lot of data. So let me see if I can get SAS fired up here. And so there should be SAS. Program, open program, chart 1. So what do we have here? Well, data landing data. Clever name for that data set. Got time, subgroup, wheel hit. This looks real similar to the data that structure that I put in my example about plastic part thickness. If you notice, what I've got here is the time point 1, 2, 3, 4, 5, 6, subgroup 1, 1, 2, 2, 3, 3. So what's my N? 2. Wheel hit 2, 9, 5, 3, 7, 2. That's the data that I have taken. That's exactly the data from my plastic thickness example, turns out. Semicolon, ends, data line. So input, these are the names of the variables, or in other words, the name of these 3 columns. First column is time, subgroup is the second column, wheel hit, the actual X variable is the third column. And data line says, okay, here comes the data, and then the semicolon says, I'm done giving you data. The run says, go ahead and execute everything from data down to run. What do? We read the data and we build an internal SAS data set called landing data. Now, as a note, SAS is kind of the standard in a lot of the finance world, because the data step in SAS is the most sophisticated system for reading problem data sets. They have the most flexibility and the biggest set of commands that you can use to read in difficult data. So we're using just a tiny portion of what the data step, as it's called, is capable of doing. So anytime you see the word data first, with or without some name and then a semicolon, what you're looking at is what is called a data step. And it's the step of reading data and creating an internal data set. So SAS has a working disk space, which is giant, because SAS is designed to run in sequence many different analyses, each analysis taking internal data that was created from a previous analysis. And so internally there is this data set. It's not really a file. It's basically a database called landing data. I'm going to turn on my ODS output delivery system graphics, and this basically I don't need, it's ignored. I'm going to run my S charts first, and then I'm going to run my X charts. So I say proc shoehart, data, landing data, this landing data, and then I run S chart twice. First time I run it wheel hit by subgroup, so the first variable before the star is the vertical axis of the chart, or the metric that you're observing. After the asterisk, this is the grouping variable. So SAS knows by analyzing this data set that my subgroup size is 2, because it's noticed that subgroup only increments every other observation. So it figures out internally what the subgroup size is. You don't have to tell it. Alpha is another way of saying false positive rate. And look, I've got 0.002. Now, if you remember back in my example, I had taken probabilities at 0.001 and 0.999 to get my quantiles. If you add up those two tails, 1 minus 0.999 is the upper tail of the chi-squared, and of course the lower tail is 0.001, you get 0.002. This alpha also says, please give me probability limits. But now I run S-chart again, and I use sigmas equals 3, or how many sigmas, plus and minus, from the mean? 3. This is the wrong way to build the chart. SAS has a hook that allows you to use the old-fashioned but wrong way to get wrong control limits. Because SAS is trying to sell software. They're not interested in reforming statistical practice. Don't use this option in the real world because it's out of date and it gives you a wrong false positive rate. Always use alpha. I am running these two to show you that you will get different control limits. Down here, though, I'm running my X charts. These are actually X bar charts. Wheel hit by subgroup, slash. The slash says, here come the options. Alpha equals 0027, which are our false positive rate, and then I say sigmas equal 3. In this case, because we get the 0027 from plus or minus 3 sigma, in this case, X chart, we will get the same exact control limits. So let's run this puppy and see what happens. So I click run, it connects to the server, it runs, it's running, it's collecting, and then boom. We've got the whole shebang here. So what do we have? Well, the S charts are first. Look at that, 13.61, and then of this, rounding to 2 decimal places, 0.01, it's really 0.005. S bar, 3.3, just like I computed in my example. The shaded blue region is the region that is good, the in-control region. See, if you're out here and here, you're out of control. That must imply that if you're inside here, you're in control. Exactly. Standard deviation of wheel hit per subgroup. Subgroup 1, 2, and 3. Oh, and notice it says alpha equals 002 limits right here. Very important. Down here, 3 sigma limits. Now look at this. 10.78 and 0. Wrong limits. Don't do this. X bar chart. Alpha equals 0027. False positive rate of 0027. 13.4, negative 4.1. 13.4, negative 4.1. 3 sigma limits. 0027 limits. Exactly the same limits on the X bar chart. So the moral of the story is, for an X bar chart, it is equivalent to set a specified number of limits that correspond to a specified false positive rate. It doesn't matter which way, but my advice to you is you want to start thinking always in terms of false positive rate. So I would always use the alpha notation to set my control limits. What I'm going to do to you in exams is I am going to change the false positive rate and have you work out control limits that work for that modified value of the false positive rate. End of screencasts for week 3.